Okay. Um, when I left off, we were talking about mesocompounds and the idea that occasionally compounds have, or molecules will have, multiple stereocenters, but they might be achiral, and we call them mesocompounds. So, how can I tell if a molecule is chiral? Um, the foolproof method is to go back to the definition, right? So, if you have an unlimited amount of time and energy, the answer to this question is build the molecule, build its mirror image, and see if they're superimposable, right? So the foolproof method is to build the molecule and its mirror image and try to superimpose them. Something about the screen with the projector is not great right now. I'm going to try and fix that maybe. Oh well, that didn't help. I'll just deal with it. So I got a question which was, do I have a mnemonic device for R versus S? I don't, but you do it enough and you remember it, I guess. But you can come up with your own mnemonic device, and for the purposes of this class, you don't need a mnemonic device because you can use your notes. So your mnemonic device is having it written down. But like anything else, you use it enough and it becomes like second nature. All right. So if I want to tell if a molecule is chiral, the definition of chiral means non-superimposable on its mirror image. But you probably don't want to have to build every molecule and compare it to its mirror image. That takes a long time. So I have kind of I don't know if you'd call it a flow chart or a sequence of steps, something you can follow here to determine if a molecule is chiral. Now, this doesn't work 100% of the time. There are exceptions to this first thing. So there are some molecules with 0 asymmetric carbons that actually are chiral, but I'm not going to make you deal with any of them. They're all kind of weird in their own ways. So I will say for this achiral here, there are a few exceptions. I just wrote we won't dead with them. That was interesting. We won't deal with them. If you're interested in how you can make a chiral molecule without having an asymmetric carbon, I can show you examples. They're kind of fun. You can build models of them if you want, but they're not all that important. So if you see a molecule that has no asymmetric carbons, you can assume that it is achiral. So what if it does have asymmetric carbons? Well, if it's an odd number, it is definitely chiral. So if it has an odd number of asymmetric carbons, you can automatically say it's chiral. So 1 asymmetric carbon, 3, 5, you can automatically say, oh, that's a chiral molecule. The question is, why is that? Well, we saw that mesocompounds have to have an even number of stereocenters because they need to have a right hand and a left hand. They need to have 2 stereocenters that match on either side of the molecule. If it's an odd number, then that symmetry is automatically broken up. So if you have an odd number of asymmetric carbons, it's chiral, you're done. Um, if it's got an even number of asymmetric carbons, that's where you have to consider, well, is it meso? And we talked about how to do that last time. First, you can say if half of them are R, if half of them are R and half of them are S, then it might be meso. But if they're not half R and half S, then it's automatically not meso, so it's automatically chiral. And then step 4 is you look for that plane of symmetry down the middle where you have the R's, every R, every right hand reflected into a left hand on the other side. And then it could be a meso compound. So that's kind of our sequence of steps for looking at a molecule, deciding if it's chiral. And again, this seems like a lot. You can have this written down and you can use it, but the more you use it, the more you'll get to know it. And you won't necessarily need a mnemonic device. And hopefully you won't need to refer to this every single time. So that's going to be our method for figuring out if things are chiral. We'll definitely do examples of it. Questions for right now? All right. So the last part of this module, and we're going to do lots of examples of this, has to do with what are the relationships between molecules. All right. So we've seen lots of different kinds of isomers at this point, and what I want to do now is classify some of those kinds of isomers. So first of all, if two molecules that have the same chemical formula, any two molecules that have the same chemical formula, meaning they're made of the same atoms, then they're some kind of isomers. All right? So basically, we're dealing with this large pool of molecules that we call isomers. All right, same atoms, different arrangements, but now we've seen there are different ways that the atoms might be, there could be different kinds of differences. So what's one way to make isomers? Move groups around, actually change the way things are bonded. All right, so our biggest category of isomers are going to be what we call structural or constitutional isomers. So our biggest subdivision among isomers is going to be into ones that have different conductivity, which are called structural or constitutional isomers, and ones that have the same conductivity, which we'll call stereoisomers. Now, stereoisomer is just this broad term for molecules that have all the same atoms, bonded connected in the same way, but arranged differently in three-dimensional space. So now stereoisomers we're going to split into two subcategories. We've already seen the two subcategories. One would be mirror images of each other. What did we call mirror image isomers? Enantiomers. So mirror images are enantiomers. So when you have non-superimposable mirror images, they're enantiomers. And then we have the others that are not mirror images of each other. So we can have stereoisomers that are not mirror images, and we have a name for those. The long name is diastereoisomers. The abbreviated version is diastereomers. So we call them. Yeah, this is the abbreviated version. Diastereomers. Diastereoisomers. So really, we just took out the iso part. It didn't save much. But I'll say I've worked with a professor who insisted on saying diastereoisomer every time, and it seems after a while, you say it 40, 50 times, you're like, wow, you've wasted a good 12 seconds today. So anyway, diastereomers, these are not mirror images. And falling into that category of diastereomers, which you might not think of right away, E versus Z isomers are diastereomers because they're not mirror images of each other. So this includes EZ isomers. So if I look at two molecules, I want to be able to identify what's the relationship between them. All right? This can be important because, as we'll talk about in a little bit, depending on their relationship, that might tell us something about how they'll behave relative to each other. It turns out things that are enantiomers will behave the same in most conditions as each other, whereas things that are diastereomers will not. So we want to be able to distinguish among all these relationships. And it's also just helpful to be able to look at molecules in different contexts and relate them to each other. All right, this is just going to be more practice with viewing molecules and getting some sense of their relationship. Just like we practice doing a little nomenclature to give us that idea of thinking systematically about molecules and kind of comparing different molecules. This is going to be one more step in that process. And this is kind of the final step. Once we get past this, and then we have one more little module with Module 9 is pretty short, then we can start talking about how molecules react with each other. So we want to be able to distinguish among these different relationships between molecules. So to determine what the relationship is, we're again going to go through a series of steps. I thought I had written them down here, but I guess I'll have to write them in by hand. So let's see, speaking of mnemonic devices, do I remember what they are? All right, first question you're going to ask is the broad distinction. Do they have the same connectivity or different connectivity? Or actually, even before that, we could say, do they have the same chemical formula? If they don't have the same chemical formula, they're not related. Maybe I'll draw this. I'm going to try and draw this in flowchart style. That's what I'm going to do. All right. So, same chemical formula. If the answer to that is no, then they're just unrelated. If the answer to that is yes, then there's some kind of isomers. Then we want to ask ourselves, okay, do they have the same connectivity or different connectivity? So if they have different connectivity, then we call them structural isomers or constitutional isomers. And if they have the same connectivity, we call them stereoisomers. So then I'm going to add in a little step there. So I have to do the same connectivity, same. I'm going to add in a little step here. Since easy isomers are kind of a trick, I'm going to add in a little step where we ask, are they easy isomers? So do they differ in arrangement around a double bond? Then they're easy isomers, which means they're diastereomers. But if they're not, easy isomers, then we have to start looking at their asymmetric carbons. We have to look at their R versus S designations. So the way to have enantiomers, it turns out, is to have all of the stereocenters inverted. So all of the R's turned into S's and all of the S's turned into R's. Okay. In order to see if two things are enantiomers of each other, they would have to have all of the R's and S's switched. So if not all of the R's and S's are switched, then they're automatically diastereomers. So another way to get into the diastereomer camp would be if some RS configurations are the same and some are changed, but not all. So now we look at RS configurations. If some are the same and some are switched, then they're diastereomers. If they're all switched, then they're mirror images. Well, if and you know what? I've been doing this flowchart thing. It's too abstract by now. I realize I should have done the examples along with it. All right. So, stop writing this down. Let's go through and do the first example. I planned the. Yeah, no, I planned this out earlier, like a week and a half ago, and now I'm realizing my plan was solid. I was going to do examples and then fill in the flow chart as I went. All right, so the suggestion is I should have left out that first step in the flow chart, but I don't think that hurt. So let me take it back. Let me start fresh. Don't worry, we're gonna fill in that flow chart, but let me start fresh. Let's do the first example. I give you these two molecules, and I say, what is their relationship? The question you would ask yourself is, do they have the same chemical formula? And the answer in this case is, well, the one on the left has a 6-carbon ring with 2 methyl groups off of it. The one on the right has a 7-carbon ring with 2 methyl groups off of it. Do they have the same chemical formula? No. So, if they don't have the same chemical formula, what can we say about the relationship? They're unrelated. All right, so no relationship. So that was step 1 here in our flow chart. Do they have the same chemical formula or not? All right, and if not, then they're unrelated. Okay, let's do another example. Take these two. I see these two and I say, all right, I want to get some sense of them. Numbering carbons is always helpful, right? Numbering carbons is a hugely helpful thing to do when you see a molecule. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, that's a decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. How do these have the same chemical formula, first of all? Yes, they do. All right. So since they have the same chemical formula, now I need to ask myself, all right, second question, do they have the same connectivity? No, they don't. One of them has a methyl, they both have a methyl group on carbon 3, but one of them has a methyl group on carbon 6, the other one on carbon 8. So, no, they don't have the same connectivity. So then we would call them what kind of isomers? Structural isomers. Or constitutional isomers. All right. So those are our first two steps on the flow chart. Do they have the same chemical formula? Do they have the same connectivity or different connectivity? Okay. Now, what if we get two molecules that we decide have the same chemical formula and the same connectivity? Like these two. All right. I see these two. Again, I'm going to number to help myself make sure I have the same atoms. So 1, 2, 3, 4, 5, 6. All right. So there's a methyl group coming off carbon 3. There's a bromine off carbon 5. So, same chemical formula? Yes. Same connectivity? Yes. Then I ask myself, all right, are they easy isomers? And the answer here is yes. So easy isomers I would classify as diastereomers. All right, this is making so much more sense now. So going back, that was our third question. So our third question is, are they easy isomers or not? All right. Making sense now? All right. Good. Let's do example 4. Example 4, I take these two. Now, first of all, they're given from a different point of view, which makes life a little more complicated. So, let me number. Where do you want to start numbering? I could start numbering at the one coming towards us, so this would be 1, 2, 3, 4, 5. This would be 1, 2, 3, 4, 5. All right. It's probably helpful to rotate one of them so that it looks like the other. So maybe I'll rotate the one on the left and redraw it. So now I would be moving number 1. Let's see. I'm rotating so that the numbering is the same. So this should be 2, 3, 4, 5, and 1. Then I have my double bond between 4 and 5. On 3 I would have a dashed, and on 1 I would have a wedge. And now I can see these are the same thing. So all of my RNS configurations are the same. So these are the same thing. All right, they have the same chemical formula, yes. They have the same connectivity, yes. They're not easy isomers. All the asymmetric carbons are the same. So these are identical. Which may seem obvious to you now. And if it seems obvious to you now, that's great. If it doesn't seem obvious, that's okay. Like, I guarantee you, most people look at these two drawings, and you, like, a month ago, 2 months ago, would have looked at these two drawings and had no idea what their relationship was. But now you can see they're identical. So I am going to add in, if all the RS configurations are the same, then they're identical. And sometimes it's obvious that they're identical, sometimes it's not. All right. So now, example 5. I look at these two. Do they have the same formula? Yes. Do they have the same connectivity? Yes. Are they easy isomers? No, there's no double bonds. They can't be easy isomers. Are all the asymmetric carbons the same? Well, I look. They're shown in the same orientation, right? One of them has 2 dashes. One of them has a wedge and a dash. So are they all the same? No. Are some the same and some switched? Yes. If some are the same and some are switched, they are diastereomers. They can't be mirror images. All right. So this goes back to my flow chart. So this was 4. This is question 5. Some same, some switched. All right. Example 6. I have these two. All right. Do they have the same formula? Yes. Same connectivity? Are they easy isomers? No. Are all the asymmetric carbons the same? No. Are some the same and some switched? No. Are they all switched? All right. So they're mirror images of each other. The last question I have, though, if they're mirror images of each other, they could still be identical. So, we have to ask ourselves our favorite question. Is it meso? All right. To determine if it's meso, remember we're going to check for R versus S. So I would go through this and say, all right, molecule on the left, priority 1, 2, 3, I'm going clockwise, this is R. 1, 2, 3, I'm going clockwise, this is R. Aha! Whereas this one over here, 1, 2, 3, this is S, and 1, 2, 3, this is S. Aha! One of them has RR configuration, one of them has SS configuration. So are these molecules chiral, or are they the same molecule? One of them has two right hands, and one of them has two left hands. Can they be the same? No. So these are chiral, and they are enantiomers. The question is, when would it be achiral? Do you think I have an example 7 up my sleeve? Yeah, probably. So the last question is, if they're chiral mirror images, then they're enantiomers. And if they're achiral, then they're identical. So let's see. Did Mr. Hamill of a week and a half ago put in an example 7? Oh, I did. All right. So I take these two. Yes, they have the same formula. Yes, they have the same connectivity. No, they're not easy isomers. Are all the asymmetric carbons the same? No. I have a dash on the left and a wedge on the right. No, they're all switched. They're not some same and some switched. All the asymmetric carbons are switched. But if I look, this one on the left-hand side has 1, 2, 3. That would be S configuration. 1, 2, 3. This would be R. Whereas this one here would be 1, 2, 3, R. This one here would be 1, 2, 3, S. Okay. So notice, yes, they're switched, but this is a meso compound, meaning the mirror image is exactly identical to it. So these are achiral, and therefore they're identical. And actually, if I just take the page, if I were to write these two down on two separate pages and take one page and just rotate it by 180 degrees, I'd be looking at the two exact same molecules. All right, we flew through that process. You're going to have to practice it a bunch. You will practice it a bunch on the skill builder, but that's it for today.